Hello students, so our topic for today is electric flux, which is a very important topic from electrostatics, and this term will be highly used in the Gauss theorem when we learn about Gauss theorem in the next section. So what is this electric flux? So first let us understand the meaning of the word flux. So basically the English meaning of flux is nothing but moving outwards, moving out, correct? So basically what is an electric flux is nothing but the number or the measure of the electric field lines passing normally through any area. Okay, so basically if you have certain area, for example this page, okay, this is your area, okay, so number of field lines which are passing through this area normally, for example these are the field lines passing, okay, which are normally passing, okay, so this will be exactly perpendicular like this, okay, the field lines passing normally. So the measure of number of these field lines is nothing but the electric flux. Let us take a simple example, okay, let's consider this is a sea over here, okay, and I'm putting a net inside the sea to catch the fishes, okay. Let us assume that the fishes are traveling directly perpendicular to this area and they are passing perpendicular, okay, to this net, okay. So let's consider these are few fish lines, okay, so these are few fish lines and the fishes are traveling like this, something like this, okay. So these fishes are traveling perpendicular, they are exactly perpendicular, okay, to the surface over here, the surface of the net, okay. So now if I want to find out the number of fishes which are passing through the area or the area of the net, okay, what would I do over here is I would simply take the area of this net. Let us consider that the area of the net is A, and I'll be considering the intensity of the fish, how many fishes are traveling throughout the journey, okay, basically how many fishes are being caught in this net, okay, that is, let's say, fish intensity, okay. So let us denote it by Fi, okay. So the number of fishes which are traveling across this area, okay, will be simply given by the dot product of these two quantities, that is Fi dot A, okay, that is the fish intensity, and area's dot product is going to give you the number of fishes traveling across this area, that is nothing but the number of fish lines, okay, let us call this as fish lines, okay. So it is going to give you the fish lines, okay. So now let us relate this scenario with our electric or electrostatics, okay. So what I'm going to do is I'm just going to convert this area, okay, into a particular area through which electric field is passing, okay. So I'll consider a area like this. I had considered earlier this as a net, correct. Now I'm considering this as a particular area, and through this area electric field lines are passing, okay. So now I'm converting my fish lines into field lines, that is electric field lines, which we have already studied, okay. Fish intensity I'm saying is my electric field intensity, so that is basically nothing but electric field E, okay, and the area, that is the area of the net, becomes the area which we have considered. So basically the number of field lines, okay, so number of this field lines, okay, will be nothing but equal to this intensity of the electric field, that is electric field vector dot the area vector. So basically the dot product of the electric field strength and the area vector is going to give you nothing but the number of field lines, okay, and number of field lines is nothing but it is the electric flux, okay. As simple as that. I'll repeat again, the electric flux through a given area held inside the electric field. So this is my area, I have held this area inside the electric field. So electric flux is nothing but the measure of the total number of field lines which or the lines of force, correct. Field lines are also called as lines of force. So it is the number of field lines or the lines of force passing normally from that area, okay, at 90 degrees. That is nothing but the electric flux. So this is your definition of electric flux. So now let us come down to the formula of electric flux, okay. So now if we consider E as the electric field, or electric field intensity. Okay, and let us consider delta S as the area, okay, through which this electric field is passing. So let's consider a area, that is delta S. Okay, let us consider a electric field which is passing like this through this area, that is E. Okay, and let us consider that the area vector and electric field are making an angle of theta. Okay, so theta, let us consider, is angle between E and delta S vector. Now here you need to understand the difference between delta S and delta S vector. Okay, they are two different things. So area, delta S, is nothing but the magnitude of the area, that is basically 200 centimeters square or 100 centimeters square or whatever. Okay, when I say area as a vector, you are going to take a direction of the area. Okay, so it is going to be perpendicular to the surface, that is, this is going to be your area vector delta S. This is nothing but the area, that is the numerical value. But when I say delta S vector, it has a direction, so it is going to be this way. So let us consider that theta is the angle between delta S and E. Okay, E is direction is this. So in this particular scenario, if you see, theta is going to be 0 because they are parallel to each other. So angle between E and delta S is 0 in this case. Okay, we are talking about general formula here. Need not be, this area need not be perpendicular to the electric field always. It might be something like this. For example, area is like this. Let's say it is little bit bent like this, and electric field is going straight. Okay, so electric field is going straight like this, okay, coming out like this, okay, and area vector is something like this, because area vector is always perpendicular. This has to be 90 degrees with the area, correct? So if I have kept my area crooked, so my area vector is going to be like this, perpendicular to the surface, but my electric field is like this. So there has to be some angle between the two here. If you see, there's an angle between the two. Okay, that angle is theta. Again, I'll repeat, supposing I have kept my area little bit crooked. Okay, I'll pick another paper. So this is my area which I have kept little bit crooked. Okay, so area vector is going to be perpendicular to the surface. So like this, it is going to be like this. Okay, and electric field is passing through the surface. So basically it is passing like this. Okay, it is going straight. So definitely between this area vector and the electric field there will be certain angle. That angle is theta. Okay, so you cannot call this angle theta as the angle between area and electric field. That will be wrong. When you say that it is the angle between area and electric field, what you are saying is it is just the angle between this plane of paper and the electric field. That is this big angle on top. Okay, which is wrong. Okay, so theta is the angle between electric field vector and area vector. It is not the angle between area and the electric field vector. Okay, that is going to be the wrong thing. Okay, so coming back to the topic here, so theta is the angle between E and delta S vector. Okay, so what is going to be the formula over here? So the flux will be given by, let's denote the flux by phi. Okay, this is the denotation for the flux. So delta phi, okay, E. Let's put, okay, electric flux is equal to E dot delta S, that is the dot product of these two vectors, okay, which can also be written as E delta S cos of theta, where theta is the angle between this electric field vector and the area vector. Okay, alright, so coming to the SI unit of this, so SI unit is going to be, we know SI unit of electric field is newtons per coulomb. So SI unit is going to be, okay, SI unit of electric field is Newton per coulomb, and SI unit of the delta S is obviously meter square. So it is going to be Newton per coulomb meter square, or you can also put it as joules meter per coulomb. Okay, this is alternate unit for it, okay, in terms of joules. Okay, so now let us see. So this is about flux. This is the concept of flux. Okay, that is, it is the dot product of electric field and the area vector, which is going to give you the measure of number of field lines passing through a particular area. Now, coming to the analysis part, there are three types of flux: positive flux, negative flux and zero flux. So let us understand what are these three categories. Okay, so let us understand what is a positive flux. So basically positive flux is the maximum flux. Let's understand that first. So positive flux is nothing but the maximum flux which is possible. Okay, flux is, I told you, the number of field lines passing through a particular area. So when will be the number of field lines passing through a particular area maximum? Obviously when the area is exactly perpendicular to the field lines. Okay, for instance, if this is my area, okay, this is my area. If I keep my area like this, okay, not area vector, area like this, and the electric field is going this way. Okay, electric field is going this way through this area. So obviously the field lines which are trying to pass through this area will be maximum. Supposing I try to keep it at an angle like this, what is going to happen? The electric field lines which are passing through the area are definitely going to reduce. Correct? And if I completely turn it this way, like the area is parallel to the electric field vector, what is going to happen? Obviously there will be no electric field lines passing through this area. The number of field lines passing through this area will be 0. So this is the simple case where we are going to see positive flux, negative flux and zero flux. So coming back to positive flux, as I told you, for the maximum number of field lines to pass through the area should be kept perpendicular to the electric field at 90 degrees like this. Okay, so what should be the angle theta here? So angle theta is nothing but angle between the electric field and the area vector. Correct? So if my surface is like this, my delta S is like this, how is going to be my area vector? The area vector is going to be like this, perpendicular. Correct? This is going to be the perpendicular area vector, right? So my electric field is coming this way out, perpendicular. My area vector is like this. So obviously theta between the area vector and the electric field is going to be 0 because they are going to be parallel to each other. Okay, if I want to try it, if I want to show it to you using the figure, if this is the area, okay, this is my delta S, let's say, okay, this is going to be my delta S bar, that is area vector, which is always perpendicular to the surface. And how is my electric field? My electric field is passing like this. So obviously theta is the angle between E and delta S, right? So angle between these two. So theta in this case is going to be 0 degrees. Okay, so let's put it in the formula. So what you'll get is electric flux is going to be E delta S cos of 0. Okay, and cos of 0 is nothing but 1. So it is going to be E delta S, that is going to be the maximum value of the flux, and it is going to be a positive flux. Okay, this is the first point. Coming to the second part, okay, so here you can also write that delta S and E are parallel, just to understand. Okay, they are parallel to each other here. Okay, coming down to the negative flux. Okay, so now my area I had kept like this. Okay, so my electric field was going out, my area vector is also going out. Okay, so for the negative flux, what I'll have to do is just flip the area this side. So what will happen is electric flux will be going out like this, but area vector will be like this, because area I have turned on this side now. So area vector is always perpendicular to the surface outwards. So you can't have area vector inwards, correct? This is the outer surface I had considered. So obviously my area vector has to be pointing this side. So it is going to go on this side like this. But my electric field would be going this way on the other side. So theta between the electric field and the area vector in this case is going to be 180 degrees. I hope you understand this. Area vector will be pointing this way, but the electric field is going this way. So they are opposite in direction. So theta in this case is going to be 180. So this is going to be your minimum flux. Okay. So negative flux is minimum flux. Okay. Wherein we have a theta as 180 degrees. Okay, how is it possible? If supposing this is my area vector, okay, let me draw my area vector on the other side now. So delta S is my area vector, which makes a 90 degrees, and electric field is opposite to it, then theta between them is 180 degrees. That is basically delta S and E are anti-parallel. Okay, so in this case delta phi E is going to be E delta S cos of 180, and cos of 180 is minus 1, so it is going to be minus E delta S, okay, which is minimum. Okay, so now understand this. Okay, delta S and delta E are parallel. Okay, that means what? Delta S and E are perpendicular. Area is perpendicular to electric field, but area vector is parallel to electric field. Same case over here, you can say delta S and E are perpendicular. Okay, electric field and area is perpendicular to each other, but area vector and electric field are anti-parallel to each other. Okay, and coming to the third category, that is zero flux. So you can very well assume that supposing my electric field is going this way, okay, in this direction, and I place my area like this, so obviously no field lines are going to pass through the area. Okay, so if I keep my surface parallel to the electric field, okay, or my electric field area vector, that is like this, okay, area vector perpendicular to the electric field, that time I am going to get a zero flux. Okay, so in this case my theta is going to be, this is the area, so this is my area vector perpendicular to the surface outwards, this is my electric field vector, so the angle between them is 90 degrees. Okay, so theta is going to be 90 degrees. Okay, if I want to draw it, the area is going to be like this. Okay, so basically my area vector is going to be perpendicular, so delta S, and electric field is going to be this way. Okay, so in this case theta is 90 degrees, so delta phi E, that is electric flux, is E delta S cos of 90 degrees, and cos of 90 is 0, so the flux will be 0. So in this case delta S and E are perpendicular, but delta S and E, okay, delta S vector and E vector are perpendicular, but area and electric field vector are parallel to each other. Okay, so this is your simple concept of electric flux. Okay, so in the next class we are going to learn what is Gauss theorem, okay, wherein we are going to use this concept of electric flux. Okay, and then later we have few derivation on the Gauss law, the applications of Gauss law. Okay, so this is it for today. I'll see you in the next class.